Today I'll be just doing a very quick video explaining essentially trigonometric substitution when taking integrals of functions for specifically calculus 2. So when I was doing this, I didn't really get a great explanation of why this worked, and I noticed some similarities between this and some other calculus things, so I did some digging around and eventually I came to this realization, and it kind of gave me a second perspective on how trigonometric substitution does work for these types of integrals. But to start everything off, I'm going to first do the derivative of arc sine of x, but I'm going to do that by implicit differentiation. So if y equals arc sine x, we know that x equals sine y. Now, if we were to take the derivative of this function, right? So with respect to x, obviously, dx of x, take the derivative here of sine y, right? This ends up with 1 equals, say, cos y, because that's the derivative of sine, times, and we'll have to do the chain rule. So the chain rule will have to do dy dx, right? And with that, then we can kind of do some manipulation with that. Divide by cos y on each side, so 1 over cos of y will then equal the derivative of y with respect to x for this function, right? This is what we get, but we don't like having this in terms of y, so might as well make it in terms of x. So we know sine squared x plus cos squared x equals 1. We can kind of apply that same principle here. So cos y is equal to, we'll do the square root of 1 minus sine squared y. And this will all equal that, right? And now we have sine squared y. This is still in terms of y, but if we look back to here, we can just plug it in x. So we have 1 over square root 1 minus x equals dy dx. And this is kind of what the principle of taking these, doing these trigonometric substitutions and how it works, because we kind of do the reverse process. Suppose we have the integral of 1 over root of 1 minus, x squared, what am I doing? But yeah, 1 minus x squared dx. In this situation, we will we'll say let x equal, in this case we'll do sine theta, right? And we'll say dx equals cos theta d theta, and with that we'll get the integral of 1 over square root of 1 minus cos squared theta d theta, and we'll make sure to keep this saying times cos theta, right? Or sorry, this is sine squared theta. My apologies. I'll write that again. Integral of 1 times cos theta over square root of 1 minus sine squared theta d theta. This can then be simplified. Cos theta over square root of cos squared theta d theta, right? And you know this will simplify just to 1 d theta, right? And with this, take the integral, you'll just have theta plus c, right? And since we have, I'll just make a note here, x equals sine theta, right? We'll have theta equals arc sine x, right? So we'll say arc sine x plus c. That would be our integral, right? And it makes sense because all we're doing is kind of reversing that process of trigonometric substitution. The only big difference would be that this thing here, where we do that chain rule, the use substitution essentially, or in this case, trigonometric substitution. We're doing substitution, and then therefore we have to add this dx equals cos theta d theta, and kind of add that to the integrand, right? But the reason we're doing that is because when we have a function, let's say f of u, and we want to take the derivative with respect to x, like let's just do something a bit sine of x squared, right? We're taking the derivative of this, so d over dx of this. We'll do the derivative of sine, so be cos of x squared times 2x, which is that derivative of that inner function, because that's all the chain rule is. And the whole point of this substitution technique of integration is when we then say dx equals this is just that derivative of that inner function, so it's eliminating that to make it a simpler integrand. And so that's the whole mumbo jumbo with finding the derivative of this function for trigonometric substitution, right? And the whole principle is you want to make it as simple as possible to make the integration as seamless as possible, just so it doesn't look as daunting as, like, it's a lot easier to integrate cos over the square root of cos squared rather than 1 over root 1 minus x squared, right? Because that just looks so crazy, unless you know, obviously. But yeah, so that just allows us to simplify it. And so an example we can do is we'll do the integral of 1 over the square root of 1 minus 4x squared dx. So off the hop, yeah, this is a pretty daunting thing, right? But how can we make this easier? Well, we can think of a trigonometric identity that looks like this: 1 minus something pertaining to another thing squared, 1 minus 4x squared. Why don't we say, because we know 1 plus tan squared theta equals secant squared theta, right? So we can then do, well, sorry, I meant to do 1 plus 4 x squared, my apologies. And this works really nicely, so what we'll do here is we'll say, let x equal tan theta over 2, right? And so essentially what we're saying is, and this we'll have to do that chain rule, the thing with the chain rule to find the derivative of it. So we'll say dx over d theta equals, it'll be 1/2 times secant squared theta. Or in other words, we'll have dx equals secant squared theta over 2 times d theta. So bringing it back to that, let's do that. So we'll have the integral of, it'll be secant squared theta. I'll just move the 1/2 to the bottom, 2 times the square root 1 plus 4 times, must be tan theta over 2 squared. Although this probably isn't the greatest, and d theta obviously doesn't look too nice, but it can be easily simplified to secant squared theta over 2 times 1. And so we're dividing by 2, but we're squaring it. This will just cancel out really nicely, so we'll get 1 plus tan squared theta d theta. I'll quickly show that here. So 1 plus 4 times tan theta over 2 squared. This will equal 1 plus 4 tan squared theta over 4. 4 cancels out, and we have 1 plus tan squared theta. I just kind of skipped a few steps. And anyways, this is a familiar identity, so we can say this equals secant squared theta over 2 root of secant squared theta, right? D theta. This will cancel very nicely into secant squared theta over 2 secant theta d theta. This will cancel off the secant thetas, and we'll end up with integral of 1/2, of secant theta d theta. This is, I'm not going to show how to do the integral here, but it is a pretty standard integral once you actually see it. But this would be equal to 1/2 ln of tan theta plus secant theta plus c. And then we've actually found both these values, or almost found, right? We found that secant theta is just what this radical is, right? And we have x equals tan theta over 2, so we can easily say x equals tan theta over 2, so we'll say 2x equals tan theta, right? So then we can just say this equals 1/2 of the natural logarithm of 2x plus the square root of 1 plus 4x squared plus c. And that is just a quick example on this trigonometric substitution. And although it looks really daunting, if you just take it slowly and just try to think a bit more rationally, it can really make it a lot easier. And this goes for not like for the substituting with secant theta, tan theta, and sine theta. One thing you might notice in later years is that you'll never sub with cos theta, right? And this is actually, it makes sense, because if you had the integral, let's say integral of 1 over, say negative 1 over square root of 1 minus x squared. This is dx. This right here actually is the derivative of cos theta, but let's try doing it with sine. We'll sub with sine. So we'll say let x equals sine theta dx equals cos theta d theta, right? So we'll say equals negative 1 over square root of 1 minus cos squared theta, right? D theta times cos theta. You can simplify this to negative cos theta. Oh my goodness, what am I doing? My apologies. Equals, so sorry, I'm rushing too much. Negative 1 times cos theta is the second time I'm doing this now. I'll say 1 minus sine squared theta d theta, right? This will equal, simplify it out, negative 1 times cos theta over cos theta. These cancel off. We'll have the integral of negative 1 d theta, which just equals negative theta. And x equals sine theta. We know then theta equals arc sine x. So, sorry, my goodness, plus c. And so we'll say negative, so theta equals negative arc sine x plus c. Now, I'm running out of space, but why is it like this? Well, I'll tell you exactly why. I'll draw it very, very, very quickly. On this plane, I believe arc sine and sine, the actual graphs, they're very similar, just one would be kind of flipped upside down. I can't remember exactly how they look. Give me 1 second. Go to this. So arc sine x looks a bit like this, and believe it or not, I'll draw here. So y equals arc sine x. And if we look at this one, this will be arc cos x. It's actually like this. Not the prettiest, but like you could substitute with cos, except you'll get this, like, they're both technically right answers. You can say equals cos -1 x plus c. These are both equally right. It's just different processes to get there, which I find fascinating. So yeah, if that ever crosses your mind, why am I only using sine and not cos? It's because arc sine and sine are essentially the same, like are such similar functions that you can find it either way. Anyways, I hope this clears up any confusion you're having like I did, and I hope the rest of your calculus journey goes wonderful.